Greetings and welcome. Okay, so today we are discussing observer theory for life science, and we are joined with Carlos and Nick and myself, James. The idea is to investigate some technical advances. Stephen has written a great blog post on observer theory specifically, so that'll be a nice introduction for those of you to understand the philosophical ideas around these sorts of things. And now we're looking at what is some code we can actually write to elaborate on these things in a more technical manner. So Nick is going to go through some of the work he's done, and then Carlos is going to give us some input from his side as well. So with that, I'll hand it over to Nick.
All right. So like I guess before sharing some notebooks, what we need some prehistory, right, to what the observer theory is and what was the introduction. Well, what was the motivation to explore it? I just remember it was started like maybe more than a year ago, just like a topic that we should certainly explore and just see what the actual observer. I remember Steven asking some ideas and even compiling some stuff about like what the general observation even means, like what are the measurement devices, what kind of devices there are. And yeah, for him, like this philosophical discussion ended up as a blog post that he did, like purely philosophical. I think it's like there is no, without any single line of code in there, which is a very rare occasion for Steven, right? So just this pure writing about what he thinks about the observer is and how to think of all about observations and measurements. For me, I tried to make it more technical, so I was just going into a literature first, seeing what people are talking about the observers and what their roles are, what their place in the theories, in the current theories, like special relativity and all that. And then I stumbled upon some nice papers with some very clear like descriptions of what an observer actually means, like in terms of special relativity. And that's how I ended up like writing some code, the actual code of those ideas applied to discrete setup that we have in the Wolfram physics projects with causal graphs and elementary observers, as I call them then. And I was going to make some kind of reminder of that and review what that thing was like 1 year ago. So that's.
Do you have references of that existing literature that you mentioned? That'll be.
For example, this one, right? I have it right there. It's like I think one of the authors that wrote a bunch of this particular idea, but even before that, it was he references this Kevin Knut guy references like Bondi K, and he's famous in some places set way of teaching the special relativity in terms of the specific interactions and way of signaling the observer, so that the observer in special relativity has even more concrete place rather than saying that there's some reference frame, right? And so just to remind what was the idea about this Bondi K calculus and Kevin Knut way of quantifying the space-time, essentially, the events on the space-time. It was all about drawing the observer and sending signals between them. So in order to, it's like describing what is the interaction in very basic, most basic terms. When the observer interacts with the system, measures the system, or some property of the system, or two observers interact, it's like depends what to describe as an observer or as a system, because they're purely relational to each other. One of them can be described as an observer and other way around. But the most basic thing is to emphasize here is that any observation that people and observers in general do when they interact or quantify something about the world around it is by this means of interaction, and this interaction happens thanks to signaling between those different places in space-time, right? And how do you actually constructively describe this type of signaling, right? That's how you can, in discrete case, I guess you can see very clearly what it is. Like here, I was just constructing some random causal graphs, just sprinkled on this diamond-shaped thing, right? When you have just a bunch of events and the causal relations, causal links between them, just based on the basic geometry, right? Minkowski geometry. So no lines more than 45 degrees there. If there is an angle between two events less than that, there should be a causal link between them, right? So that's how you sprinkle a bunch of events and draw causal links between them. So just a way of generating some causal graph in there.
Okay.
And Nick, just to clarify that. So if there's a line of less than 45 degrees and it's somehow at the shortest vertical distance or something like that, or?
Well, you can think of it like post-processing state, but you can just draw a causal link between any two pair of events that have less than 45 degrees angle between them. You draw those edges and then you get the graph, and then you can transitively reduce it so that if there like a long edge between those and there are many smaller edges, you can drop the longer edge because you already have the link.
Okay, yeah, that's what I was. That's what I was asking. Yeah, the transitive.
That's why I thought there's like there's less edges that it could be there. So it's like a reduced version of it.
It's transitively reduced. Yes, that's
yes.
The
yeah.
No.
All right, so it's like a very discrete picture of the space-time. And now you can like define some observers on them by first like indicating for this specific case, it's not like in a precise diamond when there's like one single big bang like event in the past and one common like death of the universe in the future. You can indicate like for this arbitrary graph, you can extract the sources and the sinks of the graph, right? That's what you can draw the path between them to indicate what would be the chain or the observer in this case. So essentially, you can then, by drawing these chains between those sources and sinks, you can define those as elementary observers. So any chain like that is an observer, basically, right? Or elementary observer. This is like you can think of it as a reference frame or an axis, rather as just a single axis that you draw when you draw some special relativity diagram, like this one axis going up usually by time, but here you have it in other direction, like down direction, right? So that's like a very curvy axis that you can assign to each observer, right? So this is like the same the same picture, but with actual names of the events, right?
So just to specify, the sink, is that just an arbitrary selection and then you draw in that multi-way causal path between the first node, which is the observer, and then any one of the sinks, or how are you defining which 2 points you draw in those multi-paths through?
Here's just like an arbitrary choice for this kind of graph here. Well, maybe for any kind of graph you can do this choice, but the sinks are precisely defined. Like those sources are those graphs that have in degree 0. Basically, they have no ingoing edges, and sinks are those that have out degree 0, that have no outgoing edges, right? So you can. This is like all the sinks. This is all the sources that you can just extract for arbitrary graphs, and then you can just find all the paths between them, and that's what this chains here quantified, right? So it's like this is the one of the sources, this is 190 here, this is one of the sinks over here, and there are like 2 million paths, different chains you can construct for this particular graph between this pair of vertices, right? For any other pair of vertices, there are a different number of different chains or different observers you can construct. So basically, this is like the variable that enumerates all possible observers for this particular graph, right? So that you can actually work with it. So it's not very large. Right? This is just a sample. Like you literally take like random pair of sources and sinks, and then just take sample. Nice 5 observers here. Just draw them. Right? Like this is, instead of doing this random sampling, you can do the Wuhan model thing. Nothing changes. But you have a way actually computationally or algorithmically generate this causal graph. But the same procedure applies. You can sample an arbitrary observer between some. In this case, you usually have a single initial state. So or maybe you create an initial event also artificially that creates this initial state, and from that state you can also draw different kind of observers like this, any chains, right? So you can define chains like that. This is one like another sample of just free observers in this way. You also can generalize it to multi-way systems, but you can do it in a way that, at least when you computationally do it with hypergraphs, you can, or strings or whatever, you can track one particular im or a vertex of the hypergraph or character of the string. You can track it through the evolution and basically say that, okay, whenever this particular character or a vertex appears in the event as an input, for example, right? That's the same observer, right? And that's how you can track it across multiple branches. In case there like some ambiguous event happened and split the state, but still having the same vertex on both branches. So that's how you can assign even multiple events on different branches to the same observer. But we're not gonna like describe any multi-way here now. Just like a simple idea that I don't want to talk about yet until we're gonna discuss like some quantum theory stuff later, I guess.
Okay, that's fair. Yeah.
And speculate about it, right? So it's like multi-way is all about going quantum. But just in order to describe special relativity, you just need single-way causal graphs constructed by sprinkling or single-way Wolfram model evolution. Like this is for a picture from one of the Kevin Knut's paper, right? When this idea of quantifying events based on these observer chains is described very neatly, right? So this is the picture from there, and later I tried to actually turn it into a code and actually assign those coordinates to arbitrary events and arbitrary causal, so that you can imagine that there is a function. I think I haven't finished it yet, but I think later I made this function, which is the closest you can get, I think, in the most general case to actually assigning some coordinates to events around an observer chain by maybe one line code of code away from this function, right? Like this function, for example, it's called lowest common ancestor. Actually, go to the documentation. What is it doing? So the underlying idea of quantifying any events relative to the observer becomes like the main ingredient here to actually find all the so-called lowest common ancestors of each event in relation to the observer chain. So that's function actually doing that. It's like given like this arbitrary DAG, I believe, and two vertices, like 2 and 3 here, you just find what would be the lowest ancestor or maybe closest ancestor to both of them. In this case, it returns a list because you can have like different vertices at the same distance from this pair. Like this 1 and 4 are both lowest common ancestors of 2 and 3, right?
Nick, are you showing a different page?
Am I showing just the notebook?
Yep.
Oh, sorry. I thought I was sharing the whole screen.
Your mouse is moving over this diagram in a way that it seemed like you were almost pointing at that. So yeah. Good pick up there.
Do you see the browser, right?
Okay, yeah, now we can see the browser.
Yeah, I was just showing the definition for the lowest common ancestor function. This is the graph with 2 and 3, right, vertices, and they have 2 common ancestors at the same distance. Okay?
Yeah, it makes more sense now.
Yeah, sorry about that. So you can like specify a different list of pairs or just a single vertex, and then you can enumerate all the pairs with this particular vertex, or just do it for all possible pairs on the graph, right? So that's a very common procedure if you want to then coordinatize the whole causal graph. You just assign some particular, you first find the lowest common ancestor for every pair, right? After that, you can do, I don't think I use it actually later there, but that's the function that I would use now if I would write this code from scratch. Okay. Well, okay. The first thing you do, as you can see, like you choose the observer chain. I think in this picture time goes upward. So those 1, 2, 3, 4, 5, 6, 7. You can think of those as clicks or the clock that observer have in his pocket. So just clock. So an essential ingredient of the observer has to be a clock, of some kind of way for an observer to keep track of this updating ordering of events in the graph, right? So it's not just arbitrary observer that's like a counterfactual observer. It's not yet a fully observer that computation is capable of tracking time, right? But if you can just look for those that can potentially do some actual computation work and just have at least some counter in there that just clicks whenever the new event appears. So given those clock times, clock ticks, or ticks of the clock, you can essentially then using those procedure by finding lowest common ancestor, and also not the ancestor but the reverse of it, the descendant, right? That's what this projection shows you. For example, if you pick any event not on the chain itself, right, outside of the observer itself, you can project it downwards and upwards to the observer in the future and in the past. So it's like this would be the lowest common ancestor because time goes upward. This would be the, I guess, the not the lowest, I don't know, it's still the lowest, but it's the descendant, right? So you basically need to find two events on the observer chain itself in order to quantify the event outside of this chain. That you can do for an arbitrary graph, right? So some of the events are not projected, like the 6, for example, does have a common descendant, a descendant on the chain, but there is no ancestor, so it's kind of missing one of the coordinates. So we can like ignore those events. Those basically events are that are not fully describable by this particular observer, right? If you think of those projections as some kind of radar signal that observer has to do in order to measure something about at this particular event, at this space-time location, right? It has to send a signal, that signal has to be absorbed and re-emitted, and then the observer has to have some signal received back, right? So that's like the necessary condition for an observer to actually say something about an event outside of his chain that he has a clock on, right? So those events that like maybe not particularly is like the 6. There's a signal sent to the observer and the observer received it, but it's like doesn't correspond to anything that observer sent to that event. So it's like just some noise that an observer just perceives from space that he doesn't care about. Doesn't care about like doesn't know what's the source of it. It's not bounced from any signal that an observer sent or something like that.
Is that how real radars work as well? You have to. No, I mean it's obvious to track something. You have to send out the signal and then get the response.
If you know that like this is a response to your signal, but if you just get some random response, just
you don't know who sent it.
Signal, you don't know nothing about it, right?
Yeah.
So you can drop it. So those are like events with the dots here. That those are the events that you can ignore safely, or you can't quantify those events at all.
Ambiguous data, something like that.
Yeah, ambiguous events. So you focus on all the events that have both coordinates, both clicks of your of the observer time, right? You can use those two numbers to essentially define the time distance and the space distance, right? You have two numbers. You don't know. You don't like. It's important to emphasize that there is no embedded manifold. You don't have like dimension of the inherent manifold where it happens. You have just two numbers that have the distance can be encoded relative to that observer chain. You can subtract those. For example, it makes sense to if you have 6, 2, right? It means if you subtract 6 from 2, it makes sense to assign this, or maybe also divide by 2, to assign that the time distance between this event, the observer chain, I guess, and this event is 2, right? And when you add them together, that would be like assigning a time distance. So
yeah, that's how radars work, because you have to measure the amount of time it takes for the thing to bounce to the signal to return in order to determine how far away it is.
Yeah. You basically measure this two-way speed. It's like you never know what is the one-way speed of your signal, you have to like average it out. That's why divide by 2 in that case would represent. So it's like this was the example of quantifying this 5.1 by -2 and 2. Right? I don't remember how. If this is 5.1.
You
I'm not sure why the
you minus 3 from both, and then you get -4.
I'm not sure why it's like using this 3 over here. It's like it's not a relative distance. It also assumes that this is some kind of reference point.
Yeah,
so it's
that's
not computing the distance, but the actual coordinate already relative to that 3. All right. Yeah, but you got to the way, maybe a different way of doing it. I think I've done it differently. For example, like this thing, in the end, does exactly what it says. It like quantifies all the events in that graph above relative to some observer pair rather.
Mm-hmm.
All right. I need to say this. It's like when you have a single observer, you only, as I said, you only can quantify each event by the relative distance, how far away each event from that observer, and how different the time is, right? By just adding and subtracting. But in order to actually assign some coordinate to each event, you need to at least, and maybe lay down it on some 2-dimensional space time or 3-dimensional. You need more observers, more access. Like single observer is just a single access, this time access that you can assign. You need like an additional one to do some relative to those 2 observers quantification of each event, so that they can agree on those measurements. So there are 2 observers that can measure these differences. They come together later and measure those differences. And maybe there's a third observer. You can do some kind of triangulation of their measurements, and they can actually assign some coordinates. If it's not enough, then that maybe there's 3 dimensions of space is not enough. But in our universe, 3 dimensions is enough. So 3 observers.
Is that also the minimum you need in order to make these claims? You need that third observer or that third reference?
Well, it would depend on the space-time geometry, this discrete geometry. If it happens to be enough to have 3 chains to quantify each event and they all agree, right? That doesn't matter which 3 you choose. It's like if they agree, then there's some indication that the actual space-time is 3-dimensional, right? If you just pick 2 observer chains and try to quantify your events by 2 space coordinates, it's not going to be enough. It's like some different pairs of observers not gonna agree, right? So we conclude that it's like 2 dimensions of space is not enough. So it's like very discrete way of quantifying and assigning coordinates to space-time. And it also makes it discrete by definition. It's like there's no maybe it's like very unfortunate for the infinite geometry and those claims about like that it's like fractional dimension is somehow important. But yeah, you can still quantify like to what degree they agree and all that. Maybe how can you conclude that there's actual dimensions if you average it out is not precisely 2 and 3, but based on how good is the agreement between observers, right? Right.
So is this is that a determination that you've made in the code, or is this your taken as a hypothesis, like the fact that you need these 3?
Well, I think I've done it in the code too. It's like this maybe was too obvious anyway, because I started from already by construction a 2-dimensional space time, right? The causal graph was already 2-dimensional, so you can even it's not 2-dimensional, 1 + 1, right? So it's one space. So it was enough to just have 2 pairs of observers in order to assign one single time coordinate a space-time coordinate. So you can lay all the events on this flat screen. right? So you know already a priori that it's two-dimensional.
Okay.
But
I
I could
see.
have sprinkled in on a three-dimensional manifold, and if I've done it like maybe two observers wouldn't be enough.
Okay, I
to
see what you're saying now.
assign correctly. Yeah.
So
But
in
here I
it,
was a priori knew that it's two-dimensional, and I sampled like a pair of observers. I think here it's like this says that I just took some random two observers. I generated the quantification for three observers, but I took just a pair, so that this is like it says that event number two. I think this is just those time clicks on those. This is like click. Is it? I don't remember whether they already subtracting those or not. I wrote it a very long time ago. Let me see. What are those numbers? I don't think they're time and space yet. Those are the actual, just the clicks of that clocks of the clock. But what I just trying to remember why there's just two of them. If I took two pairs, two chains in order to quantify each event. All right. It's like each of those individual chains can assign some difference. So I'm just trying to remember how this works exactly.
I mean, I understand what you're saying now about the three dimensions, just for the viewers, also maybe just to follow the way I've now understood it as well. What you're saying is, in a 3D space, it might be the case that two observations that agree are not enough to confirm where in space-time you've ended up, or like where the observation is, or at what time the observation happened. That's assuming you're in a 3D space. Then it might be that you need three confirmations. Am I understanding that correctly?
Yeah.
Vincent is asking if there is a Packlet for this.
For this one, no, really, not really. The only thing I was capable of actually like making more, making more approachable and constructive is to make this function that is useful. Even though this code, I wasn't using it at the end. But I think it could be this function can be replaced by that lowest common ancestor in order to quantify an event. It's like, let me just remember what this data structure actually represents. I think it's like for every event, it's like a list of three, because I pre-computed it for some pre-random observers that we had there, randomly chosen. I just sampled pre-random observer chains, right? Then I just walked through this causal graph, and for every event like this 1, 3, 5, for every observer, I quantified where the projection happens. So if the first pair is the list of, I guess this is the actual event on the chain, and this is the event on the. Doesn't make. What is?
Light cone ordinates for a pair of observers projections. A light cone radar. Okay.
Like this iterant term comes from Luke Kaufman, and he also has this similar idea, more algebraic idea of quantifying the events in special relativity. It just has this this nice algebraic structure also within algebra. It comes within algebra of this, when you can talk about this subtraction and adding of time clicks more rigorously.
So you mentioned before that this is a way of thinking about special relativity or general relativity. This concept
this is just special relativity now. Right? This is just a way of having all these phenomena. Like I have them later. Like maybe we can just skip this because I can't remember exactly the details of how this data structure rolls, but coordinates, like here I see that I actually do the subtraction, right? So I guess projections actually somehow determine those clicks on each of the observers. Maybe they just average it. Maybe those are just averages or something like because they're distances. Some kind of triangulation versus, but for the two-dimensional case, right? When you subtract and add them, you get the actual time and space coordinates, and you can use it to lay them. I guess this is I have a better pictures, like these guys, right? So you can, given this graph, you can now straighten out arbitrary chain corresponding to the observer, actually to make it actually to this axis, and then by computing all those coordinates for all other events that this particular chain can be like
attributed to or linked
a
to.
signal and receive a signal, right? So that all the visible events from that particular chain, you can assign these coordinates. They form this nice kind of grid, discrete lattice. You would say it's like some events are necessarily missing here, right? Because it's like there's some holes in the space-time for this discrete case. But you can do it for arbitrary observer, or arbitrary causal graph, just a concrete procedure how you can compute those coordinates.
Can I annotate something here just to see my understanding if you keep this steady? So what you're saying is like if this is the observer, then it's sending out signals at this time step, of which the only ones later on that make sense is this signal, because this is the one that received a bounce back at the later time step. So in other words, here it sent out a signal, here it sent out a signal, and then these are the signals that's returned back. So this very far one out here, this observer sent out a signal at this point, and the first time it managed to get a signal back was here, later down the line. So the fact that this took that many time steps to receive that signal back indicates kind of like how far away it is.
Yeah,
something like that.
Yeah, exactly. And you compute it by just graph distances, by just counting the number of edges, essentially, how far away that particular event is. It's like, you see, this is like the function right here, that it's the super function. I think that it's computing these pictures. It just takes this causal graph that we have, and takes some observer samples. Okay, a single observer is actually two chains. So when I say observer samples, I mean two axes. So we need two axes in order to assign two coordinates properly.
Which is the time steps and what else?
Well, t and x, right?
Okay.
If you have a single chain, you can only compute the relative distance to that chain. It's not enough to like assign some meaningful observer to the whole causal graph. If you just hand it an arbitrary graph and picking a single observer, it's not enough to assign some coordinates. If you assume it's a two-dimensional one, and two observers, two chains is enough to quantify all events nicely and they can agree on each other. You can just pick arbitrary chains, you can straighten out those axes, so to speak. One of them can be a time axis and x-axis, or they just can be like some orthogonal axes to each other, right? They can both compute the distances between to every other event, and then they come together and use those distances in order to do this two-dimensional triangulation version, and actually assign x and t, and then it can lay down the map of all events, how those observers perceive it, the space-time around them. Right. So that's how Nick,
One question, do you think that these two observers are we to imagine that these two observers are, because they are both time-like curves, right, or time-like sequences here, right?
Yes. Yeah. So any time-like sequence is an observer chain.
Yeah. So when you say you need two chains, right? Not anti-chains. Yeah.
Just chains, no anti-chain. Yeah.
Yeah. So should I imagine that as the analog of the congruence of observers that normally, in actual relativity theory, a single time-like curve or line is a particle, but an observer is actually a congruence, right? You need some thick domain where you have several parallel inertial observer line world lines, right? So to actually construct the observer. Is that what you're imagining here, or it could be just?
Oh, maybe perhaps it's like when I say that you have need to at least two chains, this like elementary time-like chains, they have some thickness to it. You can still imagine that you have some rod instead of just this chains, so that they have some thickness to those actual physical object, and you can having this thickness, it has more capability of measuring space-time around it. Because it's a parallax. It's like having two sets, like two eyes instead of a single eye, in order to determine not just the relative distance, but actually the distance is.
But this seems somehow dimensionality dependent, right? This is what you said earlier.
What is dimensionality dependent?
The number of observers that you need.
Well, that can be determined experimentally. You can say it's like here we just, because I'm doing it by construction. I'm assuming I already have a two-dimensional graph. But if I did it for two observers, I made them up, right? Maybe I took another observers. Maybe I assume that we can kind of have some repeatability in our setups of our experiments, and I lay down a different map, and they're like different. Whatever. It's like you can, by set of this experiments, you can determine, okay, it's not two observers is not enough to assign meaningful coordinates. We don't live in a flat land and not like in a single wire.
You mean, I understand. Okay, but so I would like to see how you react to what I wanted to show. I mean, what I wanted to show is mostly sort of an axiomatic recast of how normally people define Minkowski space relativity, but just to note here that that's not directly analogous to what happens in special relativity, right? Because in special relativity, one observer is enough to define a chart for the entirety of Minkowski space by definition of observer.
No, I think, yeah, you have to dig deeper into differences between those definitions. It's like, well, their definition, I think, is in terms of a reference frame. So what by observer we mean usually two lines, right? Like the whole
No. By observer, that's what I mean. That by observer normally, like in standard texts, they define observers as congruences of parallel timeline curves, right? So I mean, maybe I should just wait, and because that's what I wanted to present. That's the. And it might be that this is a point of connection, but I wanted, if it was in your head, then that's why I was asking. If it's not, maybe it will come up when I'm presenting my approach.
Yeah. Well, should we skip to your approach or just?
I don't know. No. Finish what you wanted to say. I mean, I was just.
Let me just scroll back to see. I guess there's not much more left besides like. After we establish the idea that we can actually assign some coordinates to all the events relative to some number of observers, you can also define how you can transform between those coordinates.
Yeah,
that's how we quantify all the effects, like and those k factors from Bondi k calculus very natural given those projections. Right, and they can quantify how the transformation works in the discrete case.
What is that fundamental ratio that you mentioned there?
Ratio, that's the k factor. That's another name for that k factor or radial Doppler factor.
Yeah. It's basically the relational. It's kind of a relational quantity between two observers, right?
Yeah. Like what is this projection one? That's like one way of assigning two coordinates time t and x to every event, right? And there's another one Right? There are two projections, and you can just for every event you can compute some ratios between those.
Okay.
Between time and space and time, you can compute some ratios, and that basically defines how to do transformation between them. Some natural way of doing this. So this is like a very just a concrete procedure how those events can be rated by just storing maybe quantifying some kind of relative velocity of one projection to another. All right. Okay.
We've got a comment here by Dugan. I'll just read it out. So, an observer in special relativity is a choice of basis, an assignment of coordinates in Minkowski space.
So, as Dugan, as it will become apparent, that's a consequence of definition of an observer normally, but and in many presentations it is taken as a definition of observer. But I think it's more interesting to look at observers in. That's why I wanted to present something. So otherwise, it's not that I just want to say. I have the urge to say stuff for the sake of it. Yeah.
It's like maybe the confusion here is that I'm calling the observer chain, or elementary observer is just a single axis of the whole observer reference frame, right? So you need a bunch of them in order to define an observer and quantify the whole Minkowski space time and assign coordinates to them.
That's right.
Right. So that's the difference. There's like a consequent idea is you can, given those coordinates, because they're discrete values of time and x, you can do some actual like Fourier transformations, and you can measure the energy, because if you know how the time clicks for some arbitrary chain that an observer measures, you can kind of assign some frequency to it and all kind of values to it, and that's how you would quantify energy, momentum, and mass. So that's a very simple idea of just applying Fourier transformation to ticks of those events across arbitrary chains that the observer already quantified somehow. Well, I'm not going to do the observer anti-chains. It's like some very wild idea to just try to generalize it to the multiway system. But that's basically the idea for the special relativity. How you can constructively define all those concepts and the special relativity using just the discrete combinatorics of causal graphs. Consequently, like quite rather recently, I just also found some ideas about how you can also generalize it to generalize it and come up with a general relativity. But also with actually very simple underlying idea, just the same definitions that we just went through still apply, but if you imagine this interaction of an observer sending and receiving some signal bouncing from other object or an event, right? What would happen? The underlying question is how gravity participates in all of this, right? And the underlying idea is that gravity acts as some kind of delay in this emission and retransmission of the signals. So if some object has some mass to it and gravitates, essentially, if you already have mass, and like I showed that the mass is some kind of frequency transform, Fourier transform of some signals, and depending on how much it is, if it gravitates, it also has some delay. So that delay quantifies basically. I had some picture. Let me try to find it. Oops.
James, can you let my tablet account in, maybe?
It's not waiting.
It's not?
Oh, if you go to the new link, it's got on the Discord one. I'll send it to you quickly.
It's so laggy today.
I was using the new one, I think.
There's no one waiting to get in.
I mean, it's I posted it yesterday. How do I join? Right, send me on Discord.
Okay.
That's the link I'm following.
It's so broken today. The paper pile.
Uh-oh. I'm gonna have to blur that out post stream. I'll leak the invite to the Zoom. Shh.
Is it waiting now?
No, there's no one there.
What? I mean, I'm clicking on the link and then
Does it say that you're in the waiting room?
just joins. I don't know.
Give me a second. I've just re-enabled the waiting room, so maybe try again.
Well, I found the picture that I was going to show
Okay.
of the consequence of this delay that the thing an observer observes has when it, right? You basically can quantify this delay by exactly the factor that then like acts and has a place in the Schwarzschild metric and all that. So we can derive at least have some intuition how all the general relativity comes into place by just postulating that some kind of delay acts as this curvature thing in all of your measurements by doing this radar signaling, right? So it's like a apparent delay. So it's like there is some time distance between the absorption and emission of the signal that observer sends. The observer perceives it much farther away. So that's kind of then has a consequence as all those gravitational, like the time dilation and all that.
So how would you know what that is if the only thing you do is just sending a signal and receiving a signal? How would you be able to quantify that absorption, that bounce time? That's assuming you would know from a third person perspective what those numbers really are, right?
Well, how do you know it like in the just usual? If you just send and receive a signal, you wouldn't also know the mass. You're just gonna perceive it just farther away.
I see what you're saying.
In order to actually put it on a scale, you have to like work together with a bunch of other observers, and I guess, right? So that what would be the actual like minimal procedure of weighing the thing and maybe coming up with this inertia quantity that the inertial quantity of the thing.
It makes
basically
sense.
Your mass at some kind of way of the inertia. That's also makes it a bit apparent why the inertial mass and gravitational mass is the same. It's like your inertial mass is in this absorption and emission picture. It just means how quickly it is re-emits to your signal, right? The response to your signal, that's kind of makes sense calling an inertia, right? But if it also as a gravitational part, it also has some effect of how an observer quantifies the space around it.
Yeah.
So it assigns different coordinates. So it in a way should be like assigned some curvature or whatever, like non-metricity, torsion, or whatever, some actual geometric effect. It has some geometric effect on the space-time.
I guess one way to measure that, or just the thought that came to my head at that moment, was that let's say you are receiving light from a distant star, or in this case, if it's a radar, like reflection from a distant object, and then all of a sudden there's some kind of change that takes place, like there's an object that comes in between, or there's something happens with that mass. That's how you could like measure what that effect is. So I was thinking if a black hole or something with a strong gravitational field moves in between you and the object you're measuring, you could determine the gravity of that third object by how it's changed the signal that you were receiving. Because there would be like a lensing effect, or there would be some kind of delay. You know what I mean? There would be some kind of gravitational effect.
I suspect like all of those effects can be explained by this very primitive picture of just sending a signal. Maybe it's not like very, so it's not going to be very effective because it's not has like very nice mathematical background when you just shut up and calculate all of that. But this just, at least in principle, it can be explained by this constructive radar signaling back and forth. But the actual framework of how you just make it very tight and useful, it's another whole problem. So
are you able to join, Carlos?
I don't know what's wrong with my tablet. I mean, I'm trying to. I honestly don't know what's wrong.
Are you sure it's your side?
I'm pretty sure it's here because I mean I can join on the desktop and I just go to the link, click on it, Zoom starts, and nothing happens.
You can reinstall Zoom on the tablet. Or join from the browser in Zoom, maybe. I don't know if that will be any good. Okay, interesting. So this Bondi K calculus is this idea of radar emission and receiving. That's this concept here.
Okay, I think it's working now.
Okay.
yeah, that's right.
See. Oh, okay. Twins paradox. I love paradoxes.
All right. So should I say my piece? What do you think?
Yeah, let's do it.
Okay. Let's do the whiteboard thing over here.
Mm-hmm.
Okay.
Is there a chance that we can make this a little bit more appealing?
What do you mean, like?
Yeah, that's one. Yeah, that was the main thing. Okay. So, don't have much time, but hopefully I'll be able to communicate the main idea here.
Mm-hmm.
So how we can present axiomatic relativity. Basically, the idea is you take, you begin with a set of events. This is going to be very familiar. Oops. To those who know causal set theory, it's a very similar flavor. So you begin with a set M, that's just the set of events. Then you consider two kinds of subsets. So you take a family of what you can call matter. Sorry. Oh, no. Lag again. Okay. That's not what I wanted. I wanted M to be a subset M, call this matter. And you call S a subset of M, you call the signal or light, if you want. And basically you encode what basically what Nick showed as the kind of the intuition that you have causally connected events, you encode simply as an intersection pattern of sets, right? So that means that you can think of M. I mean, this is going to be a very evocative picture, but you have to imagine that there's a bunch of set theoretic axioms to make sense of this in the background. So M is just a set. You know, you're given an event E, you might find some subset which is an M, and you might find some subset which is an S, right? And so basically the way you understand is that there's basically a light cone structure, right? That goes like that. So that's S, maybe this is S prime. This is S as well. And this is M, right? So the idea is that you assume some set theoretic axioms for MS, for the collection of all these subsets of M, right? And then you ask, okay, so these axioms, by the way, are essentially just saying that you have something like a light cone structure. So this was analogous to what Nick said, that there's let's assume that we have some causal relation, right? So I can determine whether an event here or an event here, E prime, just by the existence of these lines, whether I can define this subset, which is essentially the future of E, and see if E prime is in that subset, right?
So is it like you have a different subsets, right? So it's
yeah,
you don't have, it's impossible to have a single one, right? Just for the
you have families. Yeah, these are families of subsets. So this is families.
Well, you basically axiomatically already differentiate between matter and light, right? Somehow.
You are.
Okay.
So you're definitely distinguishing between matter and light to begin with, and you
That's
are.
Really weird. That's already seems unnecessary.
I mean, sure. I mean, we might. I mean, this is just the presentation to derive special relativity, right? So I'm not saying this is a proposal to do discrete relativity or to generalize it somehow. This is the typical presentation, right? Mm-hmm. The point is that you begin with this kind of axioms, and the axioms essentially encode the notion of a light cone, right? So imagining a light cone as a subset of events. Given an event, you have a light cone of events, right? The future light cone, the past light cone. And then you also have matter subsets, which are essentially time-like curves, right? Any time-like curve that you can imagine, right? So then in this context, so what's crucial in this context is that there are no numbers, right? The setting is so that you're just defining some set theoretic stuff. You're saying there's set M of events, there are subsets of light, there's subsets of matter, but that's it. Like I'm not saying I have a copy of the natural numbers that are next to me, or I have a copy of the real numbers, or a coordinate system or anything like that, right? You don't have any of that to begin with, and so you might want to. So there are two versions of this. You can do the very abstract set theoretic, which might be much closer to the Bondi calculus presentation that Nick did, or you can do the one that is much quicker to derive actual Minkowski space quicker. So to simplify, you might assume that M is an affine space, right? So M is affine space. of dimension D finite. Right. Just for concreteness, and in this case, yes, affine space requires. So this is a real vector space that models the affine space and so on. So yes, you have the numbers at some level, but you can take your favorite definition of affine space and dimension. So maybe you don't need real numbers necessarily if you have the right setting axiomatically. Or
So what would be your definition? Like, what is a set of points and lines? Remind us what's the definition, like the basic.
Oh yeah. The definition of I'm going to take the one that is the most direct to the actual formalism of special relativity in Minkowski space. Because here the goal is to derive. So the goal is to derive Minkowski space as a consequence of a causality structure, right? Instead of imposing Minkowski space to begin with, right? Somehow, it's like a lot of people do this by considering like some experiments that historically were relevant, like this, light bouncing off mirrors and so on, which will be very conceptually similar to what we do here. But this is more of a mathematical axiomatic presentation of that. So an affine space is a set vector space V. So this is basically the vector space of directions. And the map phi that sends, let me call it alpha actually. Alpha that sends 2 points of the affine space into the vector space. And that's the affine map. So this is the usual map that sends, PQ to what people call PQ arrow, right? So it needs to satisfy a bunch of axioms, as you can imagine. Things like, P, the pair, the diagonal, PP gets sent to the zero vector. If you send PQ and then send QR, there's a parallelogram rule that's satisfied and so on. But this is the usual idea that you have a space M that has no origin, that has no frame of reference, and all you know is that you can navigate it, you can traverse it in this way. Another way to define affine space is to say that you have a set on which there is a free and transitive action of some vector space as an additive group. But that's
can I try this specifying it over here? And what they're saying is it's a way. An affine space is like a geometric structure. It's different to Euclidean space, where there are concepts of distance and a measure of angles, in as far as you do away with all those things and you only have parallelism and the ratio of lengths for parallel line segments.
Yep.
So in other words, you only take like the information of are things parallel, and if they are parallel, what is the ratio? Like, is this double this one? And that gives you most of the same information back again.
Yeah. So, as you say, as a reminder, there is no origin, there's no metric, and there's no basis. So, right?
There is no any notion of number even, right? Because vector space, but you're including vector space, and I think it always assumes some field.
Well, that's what I'm saying. That for simplicity, assume that the vector field is over R. So this is an R vector field. So there are numbers in the definition of vector field because it's included there, but crucially, the vector field itself is an abstract vector field, right? Like numbers are included in the definition, but remember what a vector field is. Sorry, no, I'm saying field, sorry, space, vector space. It's saying field. Sorry. A vector space. A vector space does carry numbers, but think of it abstractly as an object that absorbs numbers, right? It doesn't carry numbers inside in some sense, right? You have numbers that can be absorbed by a vector. You can do 2 times a vector or pi times a vector, and that's well defined, another vector of your space. But in some sense, the space itself doesn't carry the numbers. A vector space is not like walking around saying, "Hey, number 3.5 or number pi squared," right? The vector space doesn't communicate you any numbers, right?
Just like a Boolean yes or no answer to this, right? So it's like a number, it can be just 0, 1, just saying it's like parallel or orthogonal. That's all we can do, right?
Yeah. You can define a bunch of, you can define, well, we'll see that's part of the game here. Like that's exactly the game here. There's the ingredients, the first ingredients only assume affine space. So in particular, no numbers, but also no origin, no preferred origin, no preferred sense of metric to begin with, and no preferred basis on your space. But you do have this family of, obviously we're going to use this family of matter and light subsets to do something with it. The idea is that you put, I don't have the time to do this in detail, obviously, but the idea is that you put enough effort on axiomatizing the concept of a light cone. So just abstract that a light cone is some geometric shape in 3D or 2D or whatever. Put those axioms into set theoretic terms. So basically saying, at every point you'll have a family of light rays such that they intersect in this and that way. Like there's a bunch of lemmas or a bunch of propositions that are true, right? Like, and you want to say things like, for every event there is a light cone that goes through it, and light cones at other points are defined as parallel displacements of that one because we're in an affine space, and parallelism is well defined. All those kinds of things, right? So those are the things that you're assuming. You're assuming affine geometry. You can use affine geometry in your constructions. So the idea is how to construct numbers, right? So it's similar to, it's how do we construct numbers? I mean, it might sound like a stupid question, but it's not a trivial thing to say. As you said, Nick, you have a bunch of Boolean statements like, are these two lines parallel or not? Like that kind of thing that can give you 0 and 1, but can you do better than that, right? And so the idea, and this is very summarized, and again, you would do well to look into the Bondi K calculus, sort of like the papers that do this in pasting in detail. But basically, the nature of an affine space tells me that if I take a line that I consider matter, right, the notion of signal is going to be such that they essentially model light signals, right, like in the radar model. And because I'm in a affine space, I'm going to say, well, I also have a parallel line to M, which is M prime, which is another bunch of matter that is existing in this space, right? This will be part of the set theoretic axioms that these things exist. And so what you do is you say, well, let's take some event here, E, and let's trace a light ray. So you take the unique set of light rays that go through E, right, and project up here. And this is a very familiar picture suddenly, because the set theoretic definition guarantees there is a unique E1 intersection point here, or let me call it E prime 1 over here. Then you copy the construction that you just did for E1, and then you find a unique point E2 over here, and so on, right? And here's what's crucial is that you can take any two parallel curves in your affine space with this, any two matter parallel curves, and you can replicate this construction. So you have the idea that you do this, and then you have this sort of like ladder, which is the picture of the bouncing light between mirrors, essentially, right? And so you define here E2, E4, E6, right? And this is the E prime 1, E prime 3, E prime 5, right? And so in this direction, this is a vector. You have access to this vector, right? You can define this U, which is E to E2, for example, right? That's a vector. So you can just simply say, are these two the same, right? And by, is this the same as E2 to E4, for example? So the axioms of the light rays will tell you that, yes, those are the same. And so you can you can define a sequence of numbers. You can basically say that some future ek equals some integer times the base u, some kind of unit vector that you're arbitrarily defining, simply as the idea that I send a signal, I bounce it back. It's basically the same as you were saying earlier with the signals. It's a very similar idea. But instead of, so here we exploit the structure of affine space to make this kind of construction. So this number k effectively becomes the clock, the ticking clock that you referred earlier. Let's assume that we have an observer that has a ticking clock. This is the analog of that, right? So from a purely theoretic setting where we only encapsulate the notion of a light cone and signal sending between matter objects, we encode the notion of a clock essentially by having a set of parallel lines, right? And minimally two to do this, but generally you can think that there's a family of parallel lines. And so the idea is that when you consider a congruence means a family of parallel objects, right? In some sense of parallelism, in this case, like literal parallelism in an affine space. When you take a congruence of these matter lines, so you're essentially in a affine space and you're kind of considering something that looks like this, right? At every point, you will have a light cone that has this kind of shape, right? So when you consider this kind of congruence, but you need a congruence, you need more than one matter line, then you construct a clock. So you suddenly have a way to say, if I place myself over here at this event, and I follow along my direction, because that's what I am a set of curves that has some direction, I can count time, because I can bounce light back and forth, right? Which is, if you think about it, it's a kind of when you think what a clock is physically, we always find systems that are somehow recursive, right? That somehow have some internal symmetry of what they are doing. So you can think of this bouncing light as kind of a minimal model of that idea, that you have some sort of recursivity in the dynamics of your system. But anyway, the point is that congruence in a affine space with these axioms implies clock construction. Some people call this the geometric clock construction, right? And so the idea is that if you then consider another family of parallel lines, it's just a different one, that is still matter in the axioms that you're considering, then you're going to have another sense of time, right? That congruence is going to give you a different sense of time, right? And if anyone is wondering, okay, it seems that the actual sense of time depends on the separation of the two lines. The resolution to that is that you basically choose a unit, in meaning you choose an arbitrary future event on your line, and then that's what you call u, and then you refer any particular refinement of your line is referred as a proportion to u, and that fraction, that's the fraction that you have access to in a affine space, right? You only have access to fractional relations between two vectors. But you can say that this vector is this many times this other vector. So you choose an arbitrary future event, and then you have a sequence of events. So those vectors, the u vector, which is the small one here, and the actual vectors here, will give you the k. That is basically the clock number, right? So when you have two vectors, so two unit vectors, some u and some v over here, right? These two are going to define two different units of time, right? And they are different in different directions. So the question is, how can you make this related, right? And how can you somehow implement the principle of relativity, which is, by the way, the main strength of this presentation of special relativity, in my view, is that this is the moment where you can invoke the principle of relativity. So the principle of relativity states says that u is to v what v is to u. In other words, there's no preferred observer, right?
Mhm.
Right? So that is crucial to build this, what do you call it, the K factor, or the sort of the relational
Fundamental
fraction.
ratio.
Yeah, this ratio between the two observers that then becomes the gamma factor when you do transformations and you do all the Lorentz transforms and so on. So that's one main thing. The other main thing is you notice how suddenly, if you have a vector direction, because of this construction of the bouncing beams of light, that essentially gives you a construction of the natural numbers on the future line, right? Then suddenly any vector that is parallel to this line can be measured against this unit, right? You choose some finite length as your first unit, and then suddenly any vector of arbitrary length can be compared to that. So suddenly that becomes a time-like metric, right? Because you have a way to, given a vector, produce a scalar. So you can work things out, and you see that actually that satisfies the properties of essentially a norm for future directed vectors. So you first construct the future directed norm, right? And then you do a similar thing with space-like separation. So you define your sort of space-like slices simply in terms of the light cone structure, and then you think of vectors that go along those hyperspaces or hyperplanes in your affine space, and then you define the angle between them essentially as the time distance that they will they will imply on the future cone, right? So it's very similar to what you did where in this Knuth paper, where the space-like separated things get this indices for what position they are in the observer. So anyway, the summary here, the whole point of this is that the hinge of this system is the fact that you can define numbers on a set of observers. And the crucial, why is this relevant to the observer theory project, in my opinion? This is relevant insofar that we might want to replicate this kind of construction, but forgetting, so not allowing the affine structure, right? Not allowing the fact that we have a vector space and we can count distances with relative ratios of vectors and things like that, and instead trying to come up with an analog in a causal graph, right? And I think that was very similar to what you were doing already and what this newspaper was doing. And so, but then what I wanted to clarify and try to understand was, where is this idea of congruence? Like, we need, like, a single future line, a single line doesn't have enough structure on its own, right? Like, I feel, let me formulate my thought. My thought is that the discrete setting where you have a graph, finite discrete graph, and you can count things, I think the fact that you can count by doing graph distance is an artifact. I think that is something that you can use for your algorithms, but it should not be used as the obvious definition for counts, because the fact that you can actually index things in the finite, it's almost like saying, counting the number of steps that you have along a line. It's basically like saying that you can follow along a path of light and keep track of how long it took for that path of light to travel, because you can count, you can count the number of steps that thing is taking. I don't think that's very physical, right?
No, if you think about light, then maybe, but it's I don't think it's very non-physical if you just assume that there's some kind of ticking. It's like even this picture of a single chain having a clock assigned to it. You can think of it just a coarse-grained version of whatever you drew, like here with two congruent lines and light bouncing between two chains instead, right? You can assign some mechanism to this counting if you wish to. You can imagine as if it's algorithmically constructed causal graph, you can think of those chains as counting using the hypergraph arity or whatever, just increase the arity or do whatever computational thing is required to encode this counting into a hypergraph structure, right? It just,
Sure.
you can assign some computational definitions, what this actual ticking of the clock means, but I don't think it's so unnatural thing to do.
Yeah. I don't think it's unnatural to. I mean, we have access to it, and it should be used computationally in some sense. Like it's discrete, so you can count. It's fine. But
Yeah.
to me, the worry is more about in the standard theory of relativity, right? The way that you define a clock is a construction. It's not a primitive notion, right? Like you can because I see a very strong parallel between this approach where you have just some kind of causal structure. I mean, sure, here's the two sets are separated, but you could also think that you only have matter, and then you want to impose some kind of relation of maximality or something like that. Is like the fastest matter is the same as light or whatever. But my point is, this seems to me very similar to if you just give me a set with a bunch of causal relations, right?
Yeah.
That is like saying, well, you have a bunch of events, which are the vertices of the graph, the nodes, and then there's a bunch of relations. Those are the causal links. That defines several subsets of this set, right? Like ordered subsets of this set. So in that respect, the two starting points are basically identical. Just that one assumes a background of an affine space, and the other assumes the background of a causal set with some kind of acyclic graph or something. You know, like it's basically saying we have two sets of events, and we just have two mathematical structures here. One is affine, the other is this discrete graph-like acyclic graph, whatever. So I find it
like a matter of how good your axioms are. It's like if those sets are emergent from the definition of just having relational links between events, then it seems to be more fitting to be an axiomatic theory, or the proper axiomatic construction of it, right? It's like having less definitions, then it's better axiom system then. Like in causal set theory, they said like all you need to do is just have causal relations and a notion of volume, and if you don't do the limit, if you don't take the limit, maybe even the volume is not particularly useful, right? Because you can all quantify all the events without notion of volume. Just the links are enough.
Yeah. I agree. That my only point was that I was confused in the discrete setting that there was no phenomenon, like there was no analog of the notion that an observer should be a congruence of objects somehow. Like there needs to be.
Well, you can define like a different kind of observer, so that and find only the congruent sets and only quantify relative to them. But that's just a more complicated construction to do the same thing.
Sure.
So it only needs to be the case when you want to define those clock ticks somehow from the graph structure itself. It's like maybe it seems to assign this particular natural number ticking of the clock on one particular chain. It is very arbitrary, but you can like, okay, if you want to think of everything as computational anyway, so you have to look at particular structures in our relationship that can be a clock, and you just look at for those congruent sets with something bouncing between them, and say, okay, that's has to be a clock. But it's like too complicated to have like a constructive picture of. You have to like find those or put them in like manually in order to show something concretely, right? But in principle, you can imagine I just coarse grained my causal graph so that my actual bouncing of those light between two mirrors is already embedded in the one chain.
I understand. I understand. I'm not saying that one single chain with a clock is wrong, but since you mentioned that you needed two observers in this sense, two chains to generate.
No, two axes. I call them observers, but we agreed that it's like that's just a single axis of whatever we call an observer, usually like for the reference frame that defines the whole.
But that's what I find interesting, that in this picture, right, by defining one axis and the congruence of all parallels to it, which is canonical in a affine space setting, right? That determines that what that determins is, so it doesn't determine a basis for the space, because you don't have a way to choose your actual basis for the space like, but it determines a subspace of, so it determines basically the slicing, the space-like slicing. So it's sort of the basis independent notion of the 3+1 decomposition or n+1 decomposition, right?
Well, where the tree comes from? If you just have this congruent set, how does dimension come into the picture here then? How you can quantify the whole structure of the space?
You can't. With a single observer, you can't see dimension. You just know that you are in n+1.
No, it's kind of the same thing, right?
That was my question. That was my question. If it was the same, because
I think it's basically we're saying like U and V here is just two axes, right? So with U and V, you can define at least the two-dimensional 1+1 dimensional Minkowski space, right? And assign coordinates using two vectors.
Definitely, yeah.
Right.
Yeah, definitely.
So it's like your U is just like one chain. It's just your vector needs to be defined using two chains and bouncing clock between them. You just assume that there's some congruence and actual existence of those parallel lines, right? Because you have a geometry, but they may not exist, right? You can only define them locally in some sense. Right?
Yeah. No, but that was my question. I think that's exactly what I was going to. That it might be that question of the two observers was just down to the fact that we are in at least two dimensions, because we're in 1 plus n.
Yeah.
And yeah. It might be that, yes. So it might be that it turns out to be equivalent. But anyway, it's interesting that we got to this point, because I have to go soon. Or, I mean, pretty much immediately. Unfortunately, I have another meeting, but it's interesting that we got to this point, and we can revisit after doing this recap, because we're in a similar situation to the infrageometry situation, right? Where there's a story in the more or less classical definition of special relativity from this axiomatic presentation, which I think is due to Wheeler, if I remember correctly, the first person that kind of gave this construction of the geometric clock and so on. And it's interesting because, what you can do there, you canonically exploit the structure of the affine space. You input the axioms of how signals behave, and then, in my opinion, very elegantly, you implement the principle of relativity in an explicit way. It's obvious that you can make progress to define the notion of proper time, because the notion of time is fine, but the notion of proper time, the time that is compatible between all observers and it has a good transformation property between them, that requires the principle of relativity. You can do it. You see that you have 1 degree of freedom at one point, say, okay, this could be anything. And then the only way to fix that is to say, okay, if I replicate this process, but I take V as my sort of centric observer, and I'm seeing U as my transform observer, I will have some reciprocal relation between them. And then you just have to impose that the two basically are indistinguishable. So the one and the other kind of match perfectly in symmetry. And so that basically defines a sort of a transitive property of this space. Actually, you might need to include a third one where you're doing this transitivity property. So you're in some sense encoding the group of symmetries, the isometries of the metric, or the Poincare group, or whatever you want to think about it, explicitly in this setting of like three lines, and the sort of the fact that no two lines. It might be that the principle of relativity was in fact written as U is to W the same as V is to W, and so what U is to V is, it has to be relational in this sense, right? But might actually be a second step, and the principle of relativity might really be the fact that there's no one preferred. So I just wanted to bring this up.
Just too many assumptions like already too many assumptions is hidden in this simple statement, right? What is the knowledge of those observers so that they have to be straight and inertial,
Yeah. There's a lot of assumptions, absolutely. But my point of bringing this up was not to like mimic one-to-one what this is, but more the philosophy that it will be great if all we have is some kind of causal graph, so some acyclic directed graph, right? It will be great to see if it's possible to phrase the principle of relativity there explicitly, right? That's my only point.
Well, it's possible. It's just also would require the same amount of assumptions, like some well-behaved, like subgraphs that have some actual lines, so that you can, when those observers, if you pick those observers that have quantified events so that they linearly related to each other, okay, then they're moving at some constant velocity relative to each other, right? You can define those things, but those require those additional assumptions. But if you just
I'm not saying we should define those things in the context of graphs. What I'm saying is that, to me, the principle of relativity is like all this idea that things are inertial, things are constant velocity, all these kinds of things. This is specific to special relativity. What is not specific to special relativity, in my opinion, is the principle of relativity. Right? That's something that to me should be very universal and should be found in its own guise at every implementation that we do. Because you can do this similarly for general relativity without assuming a fine space background or anything, right? So
I agree that it's like very fundamental. It just doesn't have to be so technical to involve any notion of a vector. Even it's
exactly.
It's just everything that's relational. Like every statement of one observer about something should be like relative to something should be the same as the statement of that thing relative to another direction, whatever, right? It just have to be relation.
That's totally what. Yeah. I wanted to bring this up simply because this presentation makes it apparent and transparent. Right? It makes it very clear where the principle of relativity is invoked, which is in when you have two units of time that are well defined for each congruence of lines, and you have to find a compatible translation between the two. So that's basically the summary why I wanted to bring this up. That if we do the causal structure, finite causal structure with a causal graph or whatever, it should be interesting. It would be interesting to find an example of that there. Right, where we have some notion of this is what a fundamental property of this observer defined in whichever way, finitary, local, blah, blah, blah. And this other one is finitary, local, blah, blah, blah. And there's suddenly something that has a degree of freedom that we, in principle, as the defining formalists or programmers of the system, we would have some degrees of freedom, but suddenly say, well, actually, no. We are going to impose the principle of relativity, and this is what the principle of relativity forces us to consider. That's the kind of thing that I was trying to bring in. So, if from the moment that we define observer, there's a natural line all the way to defining a system of coordinates, then I have an uneasy feeling that we did something not entirely right, because if we didn't invoke at any time the fact that there might be another observer and there might be some symmetry between them in the way they are translating their view of the world, so to speak, then I think there's still something missing. I don't think it's wrong. It's just that there seems to be something.
Yeah, sure. Well, those coordinates are defined relative to the observer. So
Right.
It's not like defying this principle at all, right? So any set of coordinates are relative to observer. So like I showed in those pictures with the green straightened out for an observer, those are just different perspective of different observers and how they assign coordinates to events around them.
Yeah.
Right?
Yeah. No, for sure. It's just that we might want to. I mean, it's interesting to me that the intrinsic property of the spacetime was only captured once you consider that translation between observers. So just in case it would be useful to bring that back again and think about this.
Now the question is how this principle generalizes to quantum theory, so that there's like now the interaction is all this relative thing about observing other system using some interaction, like using signaling or whatever. Now that it has to contain some inherent uncertainty about it.
Yeah.
Right.
Yeah, it could be just it could be ambiguity.
Yeah. There's like inherent ambiguity how the quantification happens. Not particularly of some bad information. How the observer models the information about the system, but maybe there's inherent way of the structure of the causal graph itself, maybe because it has some multi-way piece in it.
Yeah,
right?
I mean,
so the happens and the
observer's even
never knows.
It's the observer's either modeling it as quantum, or the quantum effect is not allowing the observer to model it in any other way. It's like a imposed quantum reality or something.
Yeah, it's important to understand what the actual quantum objects are when you subscribe to this relational picture, so that the actual quantum state is already relational in some sense. Some implicit observer is always in the picture when even the quantum state, like it is already formulated in the current quantum theory foundations. The quantum state is already relational. There is just has to be some observer. It's always the amplitudes of the quantum states already relative to some observer. That's the basis, and we just need to bring these two pieces together. Right? The choice of basis and the coordinate frame. It's kind of very similar in spirit, right? And we just need to recognize that the quantum state is also a relational property, the same as coordinates of the spacetime itself.
Yeah.
And even coordinates themselves are some kind of can be quantified using this uncertainty and probabilistic notions of just as some kind of informational content relative to the observer.
Yeah.
Yeah.
All right, guys, I really have to run, but I'd love to continue with the conversation next week, just to let everyone know that we are on observer theory again. Let's figure these things out. There's a very interesting intertwining pattern between causality and this notion of observer and the relativity of discrete states in a causal structure. So this will be something that we are exploring again, and now I'm going to be actively part of it as well, which is something that I was meaning to do for a long time. So yeah, looking forward to it.
I like this direction.
We more quantum, and we bring more quantum into the picture now, hopefully.
Yes. Yes. Right, everyone.
Great. Thanks so much for joining us. See you next week. Bye.